So given two sets A and B, their union is the set of elements which lie in at least one of A or B. We could define another operation where instead of looking at the elements that lie in at least one of A or B, we look at the elements that are common to both A and B. So that would be the set of elements lying in this region of overlap. And this set is said to be the set formed by intersecting the sets A and B. So this inverted U is the intersection operator. A intersected with B is the set of elements that are common to both A and B. So just as we wrote A union B as the set of all elements X such that X either belongs to A or to B or to both, the intersection of A and B can be defined as the set of all elements X such that X belongs to A and X belongs to B. So instead of an OR, we have an AND over here because X needs to be present in both A and B in order to be present in their intersection. Whereas X could be present in at least one of A or B, and that would suffice for it to be present in their union. So let's go back and consider the examples we had, and instead of taking the union, let's now take the intersection. What about this example? We have two sets A and B, and they share no elements in common. They are said to be disjoint. So what happens if we take the intersection of two sets that are disjoint? The result will be the empty set, because there does not exist any element that's common to both A and B, and so their intersection will be the empty set. Let's look at the second example where there was a partial overlap between the sets A and B. In this case, the intersection of A and B would be the elements that are common to A and B, which were the two elements 6 and 8. Then in the third example, we had B completely contained within the set A. B was a subset of A. So the elements that are common to A and B over here are the elements of the set B. So if we take the intersection of A and B, when B is a subset of A, we get the set B, because the set B has the elements that are contained in B and which are contained in A. So if B is a subset of A union B is equal to A, but A intersection B is equal to B. And we could say something very similar if we had a Venn diagram like this, where we have a universal set and any set A within the universal set. When the universal set is combined with any set A, the union will be the universal set itself. I'm indicating this U slightly differently so that we don't confuse it with the union operator over here. So U union any other set A will be U, but U intersection, when U is intersected with any other set A, the result will be the set A itself. What if we take the intersection of the set A with itself? This would also be the set A. Just like the union of A with itself is A, the intersection of A with itself is also A, because every element of A is common to both this set and to this set. So it's going to be present in the set that's formed by taking their intersection, which will be nothing but the elements of A itself. Okay, what if we take the intersection of A with the empty set for any set A? Since there are no elements in the empty set, there cannot be any elements that are common to the empty set and any other set. So the result of taking the intersection will always be the empty set. And like the union operation, we could extend the intersection operation to multiple sets. So if we have three sets A, B and C, their intersection would be the set of all elements X that are common to A, B and C. So that would be the set of all elements that are present in the region which lies in A and which lies in B and which lies in C, which is this small region over here. So if we enlarge it a bit, we can say that A intersected with B intersected with C is the set of all elements X such that X belongs to A and X belongs to B and X belongs to C. And again, the order in which we compute the intersection does not matter. We could compute first the intersection of A and B and then compute the intersection with C. Or we could compute first the intersection of B and C, take the result and then compute the intersection of that result with A. Or we could take the intersection of A and C and then take the intersection of the result with B. So the order doesn't matter. A intersected with B is the same as B intersected with A. And just as we did for the union operation, we could extend the intersection operation to as many number of sets as we like. So we could take the intersection of k sets.